Welcome to today's paper reading. Today's paper is titled Knowledge Fusion of Large Language Models. This paper, published at ICLR 2024, presents a novel approach to knowledge fusion of large language models by Fanqi Huang and colleagues from Sun Yat-sen University and Tencent AI Lab. The abstract highlights the significant costs and potential redundancy associated with training large language models, LLMs, from scratch. Instead, it proposes a cost-effective approach of merging existing pre-trained LLMs to create a more potent model. This paper introduces the concept of knowledge fusion for LLMs, aiming to combine the capabilities of multiple models and transfer them into a single, more powerful LLM. By utilizing the generative distributions of source LLMs, the approach externalizes their collective knowledge and unique strengths, potentially elevating the target model's capabilities beyond those of any individual source LLM. The approach is validated using three popular LLMs with different architectures, Llama 2, MPT, and OpenLLM, across various benchmarks and tasks. The results confirm that the fusion of LLMs can improve the performance of the target model across a range of capabilities, including reasoning, common sense, and code generation. The code, model weights, and data are publicly available for further exploration. The strategic imperative for corporations to create their own large language models, LLMs, is driven by the continuous success of models like GPT and Llama. However, the development of LLMs is associated with astronomical costs, including vast amounts of training data, advanced techniques, substantial computational resources, and skilled labor. Additionally, the development process exerts significant pressure on energy consumption and the environment. To address these challenges, this paper proposes the concept of knowledge fusion of LLMs. This approach involves combining existing LLMs into a new, more powerful model, which not only cuts the cost of initial training but also allows the integrated model to benefit from the strengths of all the LLMs. The paper explores the fusion of LLMs from a probabilistic distribution perspective, leveraging the generative distributions of source LLMs to externalize their collective knowledge and individual strengths and transfer them to the target LLM through lightweight continual training. This method emphasizes minimizing the divergence between the target LLM's probabilistic distributions and those of the source LLMs. Figure 1 illustrates the conventional model fusion techniques, which include ensemble methods and weight merging, and contrasts them with our proposed knowledge fusion approach for large language models, LLMs, termed FUSLM. The different animal icons symbolize various LLMs, with each species representing LLMs that have distinct architectures. The FUSLM approach aims to externalize the knowledge embedded within multiple LLMs and transfer their combined capabilities to a target LLM, thereby enhancing its performance across a range of tasks. In the realm of model fusion, two primary approaches have been explored. The first is model ensemble, which typically uses weighted averaging or majority voting to combine outputs from multiple models. Recently, Jiang et al. 2023 introduced a framework that leverages the strengths of multiple open-source LLMs through a pairwise comparison method. The second approach is weight merging, which involves merging model parameters at the parameter level. This method has been used to improve performance by combining models with identical structures but different configurations. In contrast, the approach in this paper supports the fusion of LLMs with diverse architectures. Regarding knowledge distillation, it involves training a student model under the guidance of one or more teacher models. This technique has been widely applied in NLP, particularly in text classification and generation tasks. The key distinction in our approach is that the target model is not constrained in size and is expected to outperform the source models after fusion. The primary objective of LLMs fusion is to externalize the collective knowledge embedded within multiple source LLMs and integrate their capabilities into a target LLM. This is achieved by stimulating the LLMs to predict the next token and assessing the probabilistic distributions of these predictions. The causal language modeling objective is used to minimize the negative log likelihood, decomposing sequence likelihood into token-level cross-entropy losses. The FUSLM approach tackles LLMs fusion through probabilistic modeling, merging the probabilistic distributions of the source LLMs. This involves a token alignment strategy to address variances in vocabulary and fusion strategies such as MINCE and average C to combine the collective knowledge of the source LLMs. The experiments were conducted using 3 representative open-source models, Llama 2, OpenLLM, and MPT. The target model for fusion was another Llama 2 7B. The dataset used for continual training was MiniPile, which includes approximately 1 million documents and 1.8 billion tokens. The fusion function employed was the minimum cross-entropy, MINCE. The performance of FUSELM was evaluated on 3 benchmarks: Big Bench Hard (BBH) for reasoning, Common Sense (CS) for common sense, and MultiPLE (ME) for code generation. The results show that FUSELM achieved an average relative performance gain of 5.16% over the original Llama 2 on BBH, 1.25% on CS, and 6.36% on ME. Table 1 presents the comparative performance of FUSELM and baseline methods on the Big Bench Hard (BBH) reasoning tasks. The results indicate that FUSELM achieves an average relative improvement of 5.16% over the original Llama 2 across all tasks. Notable enhancements are observed in specific tasks such as hyperbaton, where the performance increases from 54.40 to 65.20. However, the performance varies across different tasks, influenced by the individual strengths of the source LLMs. This table highlights the effectiveness of FUSELM in leveraging the collective knowledge of multiple LLMs to enhance reasoning capabilities. Table 2 presents the zero-shot performance of FUSELM and baseline methods on the Common Sense (CS) benchmark. The results show that FUSELM consistently outperforms the baselines across all 5 tasks, achieving a relative performance improvement of 1.25% over Llama 2. In contrast, Llama 2 CLM exhibits only a marginal improvement, with a 0.16% relative enhancement compared to Llama 2. Notable improvements from Llama 2 to FUSELM are observed in the Challenging ARC Challenge, 2.4%, and OpenBook QA, 2.71%, tasks, highlighting the effectiveness of FUSELM in leveraging collective knowledge to address intricate problems. Table 3 presents the zero-shot performance of FUSELM and baseline methods on the MultiPLE benchmark for code generation. The data reveals that FUSELM excels over Llama 2 in 9 out of 10 tasks, with a significant boost in the pass at 1 score for R, rising from 4.97 to 5.84. Additionally, FUSELM achieves an average performance enhancement of 6.36%, which is notably higher than the 1.37% improvement seen in Llama 2 CLM. This table underscores FUSELM's superior performance in code generation tasks compared to Llama 2, despite some performance gaps compared to OpenLLM and MPT. Table 4 illustrates the performance of FUSELM as the number of models fused increases. The results show that performance generally improves with more models, particularly in the BBH benchmark, where consistent improvement is observed. However, in the CS and ME benchmarks, the benefits are more pronounced when fusing 2 models rather than 3. This suggests that the performance differences among models in these tasks play a significant role in the fusion effectiveness. Table 5 presents a comparison of different token alignment criteria and fusion functions. The upper part of the table shows that the MIND method, based on minimum edit distance, consistently outperforms the EM method, which relies on exact matching. This is attributed to MIND's ability to relax the constraints of EM, effectively supplementing useful token information with minimal errors. The lower part of the table compares 2 fusion functions, MINCE, which uses a distribution matrix with minimum cross-entropy, and average C, which adopts a weighted average of distribution matrices based on cross-entropy. The results demonstrate that FUSELM with MINCE consistently outperforms average C across all benchmarks, due to the distortions introduced by the straightforward weighted summation in average C. Figure 2 demonstrates the impact of fused distributions on the optimization process in BBH. The x-axis represents the number of training tokens, while the y-axis indicates the exact match accuracy. FUSELM shows a 2.5% improvement in exact match accuracy compared to Llama 2 CLM. It achieves its best performance at 0.52 billion tokens, which is a significant reduction from the 1.57 billion tokens required by Llama 2 CLM. This suggests that the knowledge derived from LLMs is more efficiently learnable, thereby accelerating the optimization process. Table 6 compares the performance of FuseLM and Llama 2 KD, a model enhanced through knowledge distillation. Llama 2 KD shows improvements across all benchmarks compared to the original Llama 2 7B, indicating the effectiveness of knowledge distillation. However, FuseLM achieves superior results, particularly in the BDH benchmark, where it shows a 5.16% improvement compared to Llama 2 KD's 2.97%. This suggests that FuseLM's integration of multiple models through continual training yields better performance than simple knowledge distillation from a larger model. Table 7 presents a comparison of perplexity metrics between FuseLM and two other fusion techniques, ensemble and weight merging. The data reveals that FuseLM consistently attains the lowest average perplexity across various domains, indicating its superior ability to effectively harness collective knowledge from multiple language models. The ensemble method computes a weighted average of the probabilities generated by all language models, while the weight merging method integrates multiple language models into a single model within the parameter space. These findings underscore FuseLM's potential as a more efficient knowledge fusion method compared to traditional ensemble and weight merging approaches. In this study, the authors have introduced a novel method called FuseLM, which aims to create a unified model by combining the capabilities of multiple structurally diverse LLMs. This method leverages the generative distributions of these source LLMs to externalize their knowledge and employs them in the continual training of the target LLM. Through a series of experiments, the authors have demonstrated that FuseLM outperforms individual source LLMs and established baselines. Notably, in a simulated experiment featuring multiple structurally identical LLMs, FuseLM has shown competitive effectiveness compared to ensemble and weight merging methods. These findings suggest that the domain of LLMs fusion is a more promising avenue for exploration, particularly given the diverse structures and substantial model sizes of LLMs. The authors believe that these findings will inspire future research endeavors and acknowledge the support of the National Natural Science Foundation of China, the Guangdong Basic and Applied Basic Research Foundation, and the Tencent AI Lab Rhino Bird Focus Research Program. Thank you for watching.